Hey, this is Horner. We're going to start to tie together the electricity and the magnetism sections that we've done and start moving into light. So, induced fields, we said that when you have changing flux through a loop, it does induce current, but we want to know what actually causes that current. So, what's that force that pushes the charges around the loop? We know that an electric field could move charges through a conductor. So, a changing magnetic field creates that induced electric field. So a changing magnetic field does create what we call an induced electric field. So in an increasing magnetic field directed into the screen, so here we've got a magnetic field, and notice that the x's mean that it's into the screen, and we're going to say it's increasing as it's going into the screen. That induces a current in a loop that is counterclockwise in the direction. So remember, if you took your thumb and put it into the page and it got more and more electric field going into the page, then that loop will actually want to create a magnetic field that points towards you. So now you got to turn your thumb back towards you, and notice that your fingers now will coil in a direction that is counterclockwise. So we say that that induced current is caused by the magnetic field that's induced trying to come towards us. So that induced electric field must be tangent to the loop at all points to make the charges move in the loop. And so we kind of see that as we go through. So we've been through that. Here's the interesting thing, and this is new. If you have an induced electric field and it's produced by changing magnetic field, whether or not there's a conducting loop or not, so you don't really need a conducting loop for that to happen, you will still get this electric field. And notice that it does kind of circle counterclockwise, and it continues everywhere. So just as a changing magnetic field produces an induced electric field, a changing electric field will then create another induced magnetic field. Uh, if I have a changing magnetic field, it can induce an electric field in the absence of any charges, and that changing electric field can induce a magnetic field. Therefore, we can keep that magnetic or electric field sustained independent of any charge or current. That changing electric field can induce a magnetic field, which can change in just the right way to recreate the electric field, which then changes to create the magnetic field. So it's kind of like which came first, the chicken or the egg. But as long as you have an egg that grows up to be a chicken, then that chicken will then lay an egg, and then that cycle just kind of continues. So kind of a very simplified way of looking at it, but that's how electromagnetic waves actually sustain themselves. And that's why electromagnetic waves can travel through a vacuum. The light that comes from the sun travels from the sun to us through a vacuum. So there's really nothing there that needs to allow the travel of those electromagnetic waves. Sound waves, on the other hand, are a little bit different. You have to have air for a sound wave. If you clap your hands in space, nobody would hear you. And so here, these electromagnetic waves, like light, don't need any medium, is what we say, and it's because they can sustain themselves free of charges and currents. Here is a good picture of an electromagnetic wave. An electromagnetic wave is a transverse wave, and here we say the wave is a sinusoidal traveling wave as a frequency f and a wavelength lambda. So there's our wavelength going from the top to the top. The magnetic wave would also be here, so we call this an electromagnetic wave. They cannot really live independently. They've got to be together. They are perpendicular to each other and to the direction of travel, so now we do know that they are transverse waves, and they are in phase. That means they have matching crests and matching troughs. And our zeros are matching also. The speed of an electromagnetic wave is equal to 1 over the square root of the permittivity and permeability constants. So if you insert the values for each one of those, and then take 1 divided by the square root of that value, you end up with 3 times 10 to the 8th meters per second. And that is the speed of light. So yes, holy cow, you mean those two funny looking things that we've dealt with are really important? Absolutely. They are so important that they help give us the speed of an electromagnetic wave. And because light is an electromagnetic wave, we now know what the speed of light is. James Clerk Maxwell was the first to complete this analysis, and so we look at a lot of the equations that we've used so far as altogether we call them the Maxwell equations. At every point on an electromagnetic wave, the electric and magnetic fields are related. If you take the electric field and divide it by the magnetic field for an electromagnetic wave, you do get the speed of light. And so we've also talked about the speed of a wave is equal to lambda times f, or the wavelength times the frequency. And so for electromagnetic waves, that relationship becomes the speed of light. So remember, this is the speed of light is equal to the wavelength times the frequency for that light or electromagnetic radiation. We've said before, we've looked at this, but the displacement of a plane wave is the same at all points in any plane perpendicular to the direction of motion. So if I have an electromagnetic wave and it's moving directly towards me, the electric and magnetic waves should vary in time, but they should remain synchronized. So as it passes me, I would see a uniform oscillation of both of those. If it's coming towards me, I'm going to see what you're about to see here. So the magnetic wave here is pointing to the left. The electric wave is pointing up. And what I'm going to do is I'm going to fast forward through these slides so you can see how the intensity of each or the amplitude of each grows as time goes by. So that's the first one. The second one, you'll notice they're smaller, they go to 0, and then they get bigger in the opposite plane. And for each one of these, we've given it a time. So here the time is 0, here the time is t over 8, so that's 1/8. Here's 2/8, here's 3/8, and then there's 4/8, and then it would go back the other way. So you'll notice that they do get smaller and then get bigger in that other plane, and that's a pretty important thing. If that plane of electromagnetic waves moves in the x direction with an electric field moving along in the y-axis and the magnetic field in the x-axis, in the z-axis, we have a couple equations we can use. So here is the position of the electric field. That's equal to the maximum electric field, so that's the biggest amplitude, times the sine of 2 pi, and then here we have x over the wavelength minus t, little t, which is the time, and then the period down on the bottom. So same thing for the magnetic field. You'll see it's the same equation, and these are the amplitudes of the oscillating fields would be this BO and this EO. So we'll use these equations here in just a little while to kind of look. But from those equations, we can say that the amplitude of the fields in an electromagnetic wave must be related, and they're basically, you divide the two, and you end up with the speed of light. The next topic here kind of goes along with what we were doing. This is called polarization. So the plane that contains the electric field vectors of an electromagnetic wave is called the plane of polarization. So notice that the plane here is in the y direction because that is where the electric field is. This plane is what we call vertically polarized. It means that the electric field is moving in the up and down direction, and that is the vertical direction. The wave here is moving towards me, and as it moves towards me, this is called vertical polarization. If I rotate everything 90 degrees, now my electric field is in the Z and my magnetic field is in the Y, and now it's horizontal polarization. And then I can also move it, so here I've got a 30-degree polarization. So different ways of seeing how that light is, that electromagnetic wave, is polarized. Each atom in the sun does emit light independently of all the other atoms. So if I add all those up, or if I stack them on top of each other, and either that's the canceling or adding here, it's mainly going to be canceling, those waves result in, from all the different atoms, result in what we call an unpolarized wave. So light coming from the sun or most sources of electromagnetic radiation is what we call unpolarized. The energy of an electromagnetic wave does depend on the amplitude of the electric and magnetic waves. So intensity is just power divided by area. And so if I do that, I can now use a couple of new equations here to help me figure out the intensity of the electric using basically intensity from the electric field and from the magnetic field. And we're using our values that we did before for the different equations. So the permittivity and the permittability values. The intensity of a plane wave, like a laser beam, does not change with distance. So it will always be the same intensity. So the only problem is the intensity of a spherical wave, which spreads out from a point, kind of like if I have a light bulb, and we'll do a lab for this so you can see it a little bit better. It has to decrease with the square of the distance in order to conserve energy. So if the power source emits a uniform intense power in all directions, then the wave intensity of distance r is going to be I is equal to that power source divided by 4 pi times r squared. And so we'll do a lab with that one, makes it come alive a little bit better so you can see it. So if I want to double the intensity of an electromagnetic wave, I should increase the amplitude of the field by a factor of, and for this one it's going to be 1.414, and it's because the intensity is proportional to the amplitude of that electromagnetic wave squared. So I'm going to back up so we can look at these equations again, and once again intensity is proportional to the square of the amplitude of that electromagnetic wave, or the just the electric part of that electromagnetic wave. So that's where that answer comes from. Now we're going to try to synthesize things, put them all together. An electromagnetic wave is really a transverse wave. We said it's oscillating electric and magnetic fields. And so we can see the electric field and the magnetic field, and as they oscillate, if you divide the amplitude of both, you end up with the speed of light. And so the speed of light then can also tell us the wavelength and the frequency for that light that is oscillating through space. The intensity of the EM wave does depend on the amplitude, so we see those two equations. And then if I take a point source, then we can use intensity here. Here's a good example problem. This is the one we want to do. We have a digital cell phone. It emits 0.6 watts of power of a 1.9 gigahertz radio waves. They want to know what are the amplitudes of the electric and magnetic fields at a distance of 10 centimeters. So we can use that synthesis 25.1 to help us. The cell phone is really a point source, so we can use that second intensity equation to find the intensity at 10 centimeters. Once we know it, we can use the first intensity equation to compute the field amplitude so we can see each one. So here's how you would use the second equation. It's just the power of the source, so we know that that's 0.6 watts for that cell phone, divided by 4 pi times the distance, and we said that that distance is 0.1 meters or 10 centimeters. So we're ending up with an intensity of about 4.8 watts per square meter. Now I'm going to use the first equation, that first intensity equation. I've rearranged it for the amplitude of the electric field. So it's equal to the square root of 2 times the intensity over the speed of light times that permeability constant. So there we go. And once you do your work, you should end up with 60 volts per meter. Remember, that is the unit for an electric field if we're using potential indifference. We can then use the relationship between the two fields to find out what the magnetic field amplitude would be. So I know the electric field divided by the speed of light. So I'd plug in my value I just got for the electric field and 3 times 10 to the 8th for the speed of light, and I end up with 2 times 10 to the negative 7th Tesla. So that sounds like it's a pretty reasonably small value. So for comparison, the electric field due to atmospheric electricity is about 100 volts per meter. A field near a Van de Graaff generator is about 1,000 times bigger than this. And so the scale of that result seems reasonable. We don't really know. We do know that the electric field near our cell phone antenna isn't very big to produce any significant effects. So that's why we don't worry too much about it affecting your brain, even though there's studies out there that try to figure out what's really going on. So the magnetic field is even smaller than that. It's only about 250th of the Earth's field, so that means that it's not much. So you don't really have any magnetic effects while you make a phone call. So it doesn't phase in and out because of the magnetic field. Last thing we're going to do here is just do a little quick check. Typical analog cell phone has a frequency of 850 megahertz. A digital cell phone, which is the ones that we use now, are 1950 megahertz. So compared to the signal from a cell phone that is analog, the digital signal does have a shorter wavelength, but it has much higher photon energy. Because it has higher energy, you get much clearer calls. The only problem is the smaller the wavelengths that we start to use in these cell phones, the more likely that they're going to have enough energy that they could penetrate into our skull and then go through our brain, and that would be very bad. The next section we'll look at is on polarizers.